Hi, pre-calc people. We are venturing into our chapter on vectors. So let's start off with what is a vector. So a vector, like my little meme on the calendar, has magnitude, which is just a fancy word for saying length, and it has direction. It looks kind of like a ray, but usually in geometry when we drew a ray, that arrow meant it kept going. So vector, the arrow just means in that direction. So vectors, you have a tail and you have a head, and that will be important to realize when you're adding and subtracting because you have to move them around in certain ways. All right, so vector has magnitude and direction. Two vectors are congruent if they have exactly the same magnitude and are pointed in the same direction, even if they don't start at the same place, okay? A position vector. So position vector, this is kind of like parametric equations, and I think I've talked a little bit about unit vectors before. So we have here a position vector. Notice it's broken up into an x and a y component because you have a vector here, vector p, and down here on our grid, if I have a vector I, this is called a unit vector in the x direction. A unit vector, just like the unit circle, is a length of 1. That's the horizontal component. Then you have a vertical component, which we give the letter J with a little arrow. That's your unit vector. X and Y just become scalars that add to the length of the vector. So breaking it into its horizontal and vertical component, I would go over 4 and up 3. And so then the position vector coming out of the origin ends at the coordinate 4, 3. Those are the scalars that are associated with the I and J unit vectors. What you will find is I really hate writing I with an arrow and J with an arrow. So if you use a pointy bracket, you can then just put in your X and your Y, and that means the same thing. Don't use the rounded bracket, that's a coordinate. But if it has the pointy bracket, it represents a vector. A unit vector, well, I and J are unit vectors, but any vector can be turned into a unit vector if you just divide by its magnitude. And we use that absolute value to represent the magnitude. The magnitude is just basically Pythagorean theorem. So we're going to be doing it on this vector in the diagram in a second. Unit vectors are really important because you can take any vector, say it represented a force, and I can control what I want that force to be. If I first turn it into a unit vector, I can then multiply by any scalar. And so by multiplying 1 by anything, I can make it be the length that I want, or the direction if I want to make it negative. So unit vectors are pretty powerful. Then we have the opposite of a vector. The opposite of a vector just means you're going in exactly 180-degree direction. So if I had a vector p, the opposite would just be negative p. That's important to know because when you do subtraction of two vectors, you're really adding the opposite. All right, so let's do some example here. Write vector p in terms of its components. So notice you would go over 4 and up 3. So I could write vector p as 4i plus 3j, which I find really annoying. So I tend to prefer to write it with the pointy brackets, the vector 4, 3, which is where it would end. Find the angle that P makes with the positive x-axis. So that's looking for this angle down here. So what I could do is you can notice here you have a right triangle. I would stick with always doing tangent just because you don't have to really think about too much. Tangent is opposite over adjacent. So that's going to be the y value over the x value. Just remember, again, if your vector ends in the second or third quadrant, you're going to have to add 180. But just like before, whatever you get, so you want to be in degree mode, round it to the nearest angle. All right. Now, we want to find the unit vector for P. So the unit vector represents P over the magnitude of P. So let's first find the magnitude of P. So that's just Pythagorean theorem. So 4 squared plus 3 squared, it's a 3, 4, 5 right triangle. And so to represent the unit vector, you just then take your vector and divide each element by the magnitude. So it would look like this. Now, how do I know that's truly a unit vector? I could do Pythagorean theorem on it. If I did 4/5 squared plus 3/5 squared, notice I get 16 plus 9 on top over 5 squared on bottom, and it is truly a unit vector. It's a vector of length 1. Now, find a vector of length 8 in the direction of P. So that means since I already have my unit vector, I can now control its magnitude by just multiplying 8 times my unit vector, which is multiplying 8 times 4/5 and 3/5, and I end up with 32/5 and 24/5. That would be the final answer. And if you want to do a Pythagorean theorem on that, it should end up being 8 since you're multiplying it by 1. We already verified that our unit vector is 1. Then lastly here we have find the opposite of P. So this one's really hard, guys. Just multiply by a -1. There we go. All right. So there's the basics of a vector for us for right now. Now let's look at doing some operations on these. So there's a lot that's going to be happening on this little grid down here. So you have a vector sum, A plus B, which means you're going to take the tail of B and put it on the head of A. Basically what you're doing is, it's like trying to describe someone who has to walk in strictly XY direction, and then once you're done with that vector, you start from where you ended and keep walking. Walk the X, then walk the Y. I don't know if that made sense. My brother had to do this in the Air Force Academy. To walk across the quad, they could only walk in like an X and a Y direction. They could never walk diagonally. It's kind of crazy, but whatever. All right, so here's vector A. Let's go ahead and put that on our grid. So 3 and then 4. So 3, 4, I usually like to find where it ends, and then just draw a vector coming out of the origin that ends there. And I'm going to do B. I'm not going to label things because it's going to get looking really busy there, so I'm just going to try and color code. B is 4, -2. So we'll go out to 4, down 2. That would be A and B as position vectors. Position vectors come out of the origin. All right. Now, if I want to find A plus B, algebraically, all you're doing is to find the sum of two vectors algebraically. You're just adding like components. So 3 plus 4i plus, let me see, 4 minus 2j is going to leave me with 7 comma 2 is where that would end. But if I'm going to do it graphically, let's take a look at what happens. So A ended, I went out 3, I went up 4. B says go out 4, so I do it from where A ended at its head. And so now I'm going to go 1, 2, 3, 4, and down 2. So basically what I have done is I've taken my vector B and I've translated it. I slid it up to the head of A, maintaining the magnitude and the direction. The resultant vector, you go back to the origin and draw from where you first started to where you end. So we tend to represent our resultant vector with R. And that's how that would look. All right. Now let's take, also notice, because this is just worth doing anyway, if I had done B plus A, that would tell me to go out 4, down 2, then it would tell me to go out 3, 1, 2, 3, and up 4, 1, 2, 3, 4. I would end at the same place. So notice that addition is commutative. It basically makes a parallelogram, and the resultant vector is the diagonal of that parallelogram. If I'm going to do A minus B, this really represents A plus the opposite of B. So what we're really doing is taking 3 minus 4i and 4 minus a negative 2j. So that would end me at negative 1, 6. Whoops. Oh my gosh, hang on. My neighbor's trying to get me to go for a walk, and I'm going to try and ignore her because I don't want to have to start over again. All right, so there's A minus B, would take me at negative 1 and up to 6. But let's see how we would do this graphically. I'm going to take my A, so A stays the same. Here's A. And then if I'm going to do the opposite of B, so the opposite of B is negative 4. Notice I'm going to go, what color can I use now? Let me use pink. So from the end of A, I'm going to go 1, 2, 3, back 4, and up 2, right? So here is, notice that B went exactly, this was B before, this is opposite of B. So my resultant vector is exactly where we said it would be. It's at negative 1, 6. Dad, give me 10. Okay, so I'm at negative 1, 6. Sorry, I just wanted to let my neighbor know I'll come out in a minute. So okay, so subtraction. It's A plus the opposite of B. If you figure it out algebraically, it kind of helps, but to see it graphically is important here, as you'll see in a second. So now what we're going to do is draw the displacement vector that goes from B to A. All right, I know you're like, this is getting kind of crazy. So you know what I might do? Let's do this. Let me make another grid down here. So I had vector A, that was my vector 3, 4. I had vector B, which was going out 4, down 2. Going out 4, down 2, so it kind of came out like that. Those are as position vectors, right? So now what I'm going to do is I'm going to draw a displacement vector. Displacement vector is just a vector that goes from the head of one vector to the head of one vector to the head of the other. And they do not have to be in standard position necessarily. They can be anywhere. So if I'm drawing the vector that goes from B to A, so this is the vector that goes from B to A, what you should notice, and here, this is going to be really crazy, I'm going to draw it in hot pink. Right there. That's the vector we're trying to draw. I want you to notice that that is the same vector as the one that was the resultant vector B minus A. Now remember, vectors are congruent if they have the same magnitude and the same direction. So even though they started at a different place, this vector, I just hit something I'm not supposed to hit, is B was A minus B. This was A minus B. That was equivalent to the displacement vector from the head of B to the head of A. Now, how we write this is, that's like saying find the vector that goes from the head of A to the head of B. That's how I would write it. But notice, what does that represent? That represents A minus B. It's like the opposite. All right. That is the vector that goes from the head of one to the head of the other. To go from the head of B to the head of A is A minus B, and that's because minus B was back here, and A minus B then went out here. Oh, what am I doing? And then we did the A, came out here. There was A, and those two vectors have the same length and the same direction. All right. Okay, now we have vector 5A plus 9B. All right, so this is just a matter of multiplying by a scalar. So it's 5 times, and I'm going to use my little vector notation, 3, 4 plus 9B, which was 4, negative 2. I'm not going to put that on the grid because that's going to be really big. But that would be basically you're adding 15 and 20 to 36 and negative 18, and the result would be 51, 2 is what that vector would be. So you're just multiplying each by a scalar, and again, add like terms. Now, let's look at what's going on down here. Find the magnitude of A plus the magnitude of B, and then find the magnitude of their sum. So let's see how this works out. The magnitude of A, hopefully you realize that's again a 3, 4, 5 right triangle. The magnitude of B is going to be the square root of 16 and 4, square root of 20. Okay, so adding those two together, this is about 4.47. So that would give me about 9.47. Now A plus B, we have this up on top. Remember that A plus B was 7, 2. That was up here. So the magnitude of A plus B is going to be 7 squared plus 2 squared, which is 49 plus 4 is square root of 53, which is about 7.28. And so notice that these are not equal. Never. It is not, that magnitude is not distributive. Okay, this is a little bit hard through a video, but I hope that made sense, and we're going to keep working. Okay, so to kind of pick up on what we ended with on the previous page, displacement vectors versus position vectors. So remember that a position vector is a vector that comes out of the origin. So that would be an example of a position vector. A displacement vector can be any two vectors, doesn't matter, they do not have to start off being position vectors, any two vectors. The displacement vector is the vector that goes from the head of one to the head of the other. So like I said in the other one, so let's say this was A and this was B. The displacement vector that goes from the head of B to the head of A, that's my displacement vector, that's how I would write it, actually calculates as A minus B. So remember, it was a matter of, you could translate A minus B and you would get the same magnitude, same direction, and so that's a shortcut for finding that displacement vector. All right, so what are we going to do with this? We're going to be using these displacement vectors a lot throughout this chapter. So we're given 2 points, 4, 12 and 10, 6, and we want to find the vector CD that goes from, again, the head of C to the head of D. And I'm actually not going to even draw them. So if I'm looking for vector CD, that represents vector D minus vector C. It's always kind of the opposite. So again, remember, you're just subtracting like terms. So this will be 10 minus 4 here. And then this will be 6 minus 12. So that displacement vector would end at 6, negative 6. That would represent the displacement vector. All right. Now, we want to find a position vector of a point that is 3/4 of the way from C to D. This gets a little bit tricky, all right? So how would we work this out? We want to, oh my gosh, this is so much harder on a video than just kind of doing it in person. Sketch a vector starting at point C. So what I'm going to do is let's put our vectors on our grid just so we can kind of see everything. So vector C is 4, 12. So I'm going to put that down on my grid here. 4, 12. So see if I can draw a straight line out to that. So there's vector C. So I'm going to do vector C in orange now. I will do vector D in green. That one is 10, 6, 10, then go up 6. So here is vector D. And if I want the vector that goes from C to D, notice the direction here. It is going from the vector C to the vector D. Remember that was C, this is D. This is the vector from C to D, which represents D minus C. Ah, a lot of letters, I know. Okay, now what they want us to do is they want us to find a position vector, so it's got to come out of the origin, that ends 3/4 of the way from C to D. So I'm just going to guess right now it's somewhere in this neighborhood. So if you start from C and go about 3/4 of the way, actually I don't think I went far enough, that's the idea. We want to find the position vector that's going to come out. I'm not sure where yet, but it'll end somewhere in this neighborhood. Okay? How do we find that? Well, you're going to go along a path. So it's kind of like someone telling you, walk so many spaces in this direction, then turn a certain degree. We did bearing. It's kind of that same idea. So notice that the path that you are going to take is going to be, you're going to go, how do I draw this? I need a new color. Let me find a new color here. I'll do it in yellow. Here's the path you're going to take. You are going to walk out along C. Then you're going to turn and you're going to walk 3/4 the distance along CD. And wherever that lands, you would then go back to the origin and draw your resulting vector. So it's actually vector addition that gets you to the position vector we're looking for. So the first thing some people do is find 3/4 of the way from C to D. So that would be the equivalent of multiplying the vector we found up above by 3/4. So when I do that, let's see here, we have ourselves 18 divided by 4, which reduces to 9/2, and then negative 18 divided by 4. So I guess you could write this as 4.5, negative 4.5. All right, that would be where we would end. But we want to show how to get there. So how you get there is you have to go along vector C, and then you add to that 3/4 of the vector that went from C to D. So what that gives me, C was 412, and we are adding to that 4.5, negative 4.5. So that's going to leave me at 8.5 and 7. 12 minus 4 is 8 plus another negative, so that's going to leave me at 7.5. Well, let's see how our approximation went. So we want to go out to like 8.5 and up. Whoops, 8.5 is here. 7.5 is about here. Wow, look at that. I was almost spot on. Boom! That would be our position vector. So if we labeled this R, that is the result of going, that is the position vector that goes 3/4 of the way from vector C to vector D. So let me just walk you through this again. To find a displacement vector That's just from head to head. If you want the position vector, again, from the origin, that ends a certain fraction of the way along your displacement vector, it's actually vector addition. You have to go along the path of the one vector, and then you add to that fractional distance, fractional magnitude, that tells you where your position vector will end. Then you go back to the beginning and you can draw your vector to that tail. So for the 3/4, it was C plus 3/4 CD. Hope that made sense.